Equivalence relation. Definition. An equivalence relation on a set S is a set R of ordered pairs of elements of S, such that for any A from the set S, the pair AA is in R. This is called reflexive property. If AB is in R, then BA is also in R, symmetric property. And if AB is in R and BC is in R, then AC must be also in R, transitive property. So any relation on the set S, which is reflexive, symmetric, and transitive, is called equivalence relation on the set S. When R is an equivalence relation on a set S, it is customary to write ARB instead AB, the pair AB belongs to R. This means the same as this. A is in relation R with B. Also, since equivalence relation is just a generalization of equality, a suggestive symbol such as approximately equal, congruent, and this is usually used to denote this an equivalence relation. If this is an equivalence relation on a set S and A is in S, then the set denoted this way, it is we say that this is the set determined by A. Equivalence class determined by A is the set of all X in the set that are in relation with A. So this set is called the equivalence class containing A. Here we have an example of an equivalence relation on the set Z of all integers, congruence mod 5. Because any integer is congruent to itself mod m, the relation is reflexive. A congruent to B mod m implies that B is congruent to A mod m. Yeah, both numbers have the same remainder mod m. So the relation congruence mod m is transitive, reflexive, symmetric here, and then it is transitive because A congruent to B mod m and B congruent to C mod m implies that A is congruent to C mod m. Of course, A and B have the same remainder mod m from here. B and C have the same remainder mod m from here, which means that A and C must have the same remainder mod m, so they must be congruent mod m. So, relation mod 5 in the set of all integers is an equivalence relation. The class of 1 consists of all integers that are congruent to 1 mod 5, and one can see that the class of 1 is the set of all integers that can be written in this form, 5k plus 1, where k is any integer. The next topic here is a partition. A partition on a set S is a collection of non-empty disjoint subset of S whose union is S. Of course, here S must be not empty from the beginning. For example, if S is the set of the numbers 0, 1, 2, and 3, we can form a partition this way. Take this subset, say 0, 1, and then 2, 3. These two subsets form a partition of S because they are disjoint. The intersection is empty. And their union is equal to the whole set S. Of course, all the numbers are in the union. So these two subsets of S form a partition of S. S may be infinite set, and the definition still holds. For example, Z is infinite. There we also can have partitions. And we have this theorem about the equivalence class of partition of an equivalence relation. It turns out that they corresponds to a partition of S. The equivalence classes of an equivalence relation on a set S constitute a partition of S. Conversely, for any partition P of S, there is an equivalence relation on S whose equivalence classes are the elements of P. We know that congruous mod 5, this relation is equivalence relation in Z. So the equivalence classes of this relation must form a partition of Z. What are the different equivalence classes? The class of 0 consists of all multiples of 5. The class of 1, all numbers that have remainder 1, mod 5. The class of 2, all numbers with remainder 2. The class of 3, all integers with remainder 3. And the class of 4, all integers with remainder 4. Obviously, these are disjoint classes, disjoint subsets, and their union is the whole set Z. Obviously, the union is a subset of Z. Yeah, all these sets are subsets of Z, so the union will be a subset of the set of all integers. To prove that they are equal, we have to show that any integer belongs to this union. So let m be any integer. Then we divide m by 5. We get a quotient and a remainder. And by definition, the remainder is a non-negative integer strictly less than 5. So R is one of the numbers 0, 1, 2, 3, and 4 in that case. So the class, R, this means that M belongs to the class of R, which is 5k plus R, M. This is one of these numbers. And R is one of these sets, so we prove that Z is a subset of the union of the subsets. And having two opposite inclusions, we conclude that they are equal. Z and the union are equal.